Hey, welcome. We hear all the time about how AI is going to completely change medicine, right? But what happens when these super smart algorithms leave the perfect, clean lab and get thrown into the messy real world of a hospital? Well, today, we're diving into a huge blind spot in medical AI, one that has massive implications for how we understand brain health. So, take a look at this scan. You see those bright white spots? You might think it's just, noise or a glitch in the image, but they are actually incredibly important warning signs. And for a long time, our best AI tools have been, believe it or not, kind of terrible at seeing them clearly. So, what exactly are they? And more importantly, how do we fix the AI's vision problem? So, here's how we're going to break it all down. First, we'll get into what these bright spots are and why they're such a big deal. Then, we'll explore why current AI just chokes when it sees them in the wild. After that, we'll see how researchers built a better test, check out two really cool new solutions, and then wrap it all up by talking about what this means for actual patient care. All right, let's jump in. Section 1, bright spots, big concerns. Before we can figure out why the AI is failing, we've got to understand what these little spots are actually telling us about what's going on inside our brains. Okay, so the official name for these is white matter hyperintensities, or WMHs for short. The easiest way to think about them is like signs of damage on the brain's tiniest blood vessels. The microscopic plumbing that keeps the whole system working. When that plumbing starts to get worn out or damaged, these bright spots pop up on an MRI. And here's why this is so critical. These are not just random blemishes on a scan. The number and size of these WMHs are directly connected to some really serious health problems. We're talking about things like cognitive decline, a higher risk of dementia, and even an increased risk of stroke. So yeah, being able to measure them accurately is a very, very big deal. And that brings us right to the heart of the problem. We have all this amazing AI that's supposed to help us, but it hits a wall the second it steps out of the research lab. This is where a perfect algorithm meets the messy, unpredictable reality of a busy hospital. Now, you might be thinking, well, why not just have a human expert, a doctor, measure them? Great question. But the thing is, manually drawing circles around these spots on scan after scan is incredibly slow and tedious. Plus, even two different experts looking at the very same scan can come up with different answers. It's the perfect job for a super fast, super consistent AI. If we could actually get one that works. And here's exactly why they so often don't work. The best analogy is a professional photo studio versus random snapshots on your phone. Most AIs are trained on research data, which is like the photo studio. Everything is perfect, standardized, same camera, same lighting. But clinical data from a real hospital, that's the candid snapshots. All different cameras, different lighting, some are blurry. It's just messy, and that mess completely confuses the AI. And hey, don't just take my word for it. This quote from the research paper just nails it. The models that seem brilliant when they're looking at those perfect studio quality images just completely fall apart when you show them the real world stuff from actual patients. And that's a massive problem if you actually want to help people in a clinic. Okay, so what do you do? If the old AI models are failing the real world test, how do you build a new one that can pass? Well, the researchers knew you couldn't just start coding. No, first you have to build a better test. You need a benchmark that actually looks and feels like the real world. And that is exactly what they did. They went out and gathered 195 brain scans. But these weren't pristine lab images. These were routine, everyday clinical scans, the kind of stuff a hospital radiologist sees all day long. Then experts went through and painstakingly marked out the WMHs on every single one, creating a new gold standard. Now here's where it gets really important. Those 195 scans didn't just come from one machine in a basement somewhere. Nope. They came from 71 different MRI scanners. That incredible variety is the exact kind of real-world messiness that makes older AIs just give up. And it wasn't just a bunch of similar scanners either. They made sure the scans came from 4 of the biggest manufacturers out there. Think Siemens, GE, Philips, Toshiba, the whole shebang. This new data set was designed to be the ultimate stress test, perfectly mimicking the mix of technology you'd find across tons of different hospitals. So with this new, super tough benchmark ready to go, it was time for a showdown. Could a new approach to AI finally succeed where all the others had failed? The researchers decided to test out 2 very different paths to find a solution. First up, the old guard. They took the existing state-of-the-art AI models and ran them against this new, messy data set. And the result? They failed, big time. The researchers said they showed poor generalization, which is a polite way of saying they just couldn't cope with the real-world data at all. And check this out. This slide shows you how they failed. It wasn't just that they were a little inaccurate. Oh no. Some models, like LST-LPA, kept confusing a totally normal part of the brain for a dangerous lesion. Others, like WHM-SynthSeg, were basically seeing ghosts, creating huge blobs of fake spots that weren't there. And another one just flat out missed most of the real damage. A total mess. All right, so out with the old and in with the new. Let's meet our two new contenders. First, we have the Specialist. This AI was built from the ground up and was trained only on that tough, messy, real-world data. It became an expert at one very specific, very difficult job. Then we have the Quick Study. This one is different. It's a huge general-purpose medical AI that was just given a little bit of coaching to get it ready for this specific task. And the results? Whoa, the Specialists absolutely crushed it. It scored a 0.768 for accuracy. Just look at the chart, it's towering over the older methods. That old LST AI model, it scored a measly 0.423. It's not even close. This proved that training on messy, real-world data works. So the Specialist proved it could be accurate. That's awesome. But our other contender, the Quick Study, had a totally different kind of superpower, and it was all about speed. And this is where the future of medical AI gets really exciting. So how did it learn so fast? The process is actually beautiful in its simplicity. You start with this giant AI brain, a foundation model called MedSam that already knows a ton about medical images in general. Then you just show it a handful of examples from our new messy dataset, basically saying, hey, this is what we're looking for. This is called fine-tuning, and it lets the AI adapt its huge knowledge base to a new problem with almost no effort. And when I say minimal effort, I mean it. How many times did they have to train the model on the new data? 1,000 times? 100? Nope. Look at this number. It's 1. It took just a single pass through the data for the model to reach a really impressive level of accuracy. Just 1. That is the incredible power of building on a solid foundation. Which brings us to our final section. What does all of this actually mean for us? How does this cool research jump from a science paper into your doctor's office? And what's the real impact for patients? All right, let's wrap this up. Here are the big takeaways. Number 1, and this is the most important. If you want AI to work in a real hospital, you have to train it on real, messy hospital data. 2, those two new successful models, our Specialist and our Quick Study, they're now out there, publicly available for anyone to use and build on. 3, these huge foundation models are a total game changer, giving us a massive shortcut to creating powerful, specialized AI. And finally, this whole project gives us a clear roadmap for how to make AI a truly reliable tool in day-to-day healthcare. And that leaves us with one final thought. We started by talking about what those little white spots really mean. They're warnings, signals of risk for stroke, for dementia. By finally teaching an AI to see them clearly, reliably, no matter what hospital you're in or what scanner they use, we're not just solving a computer science problem. We're building a tool that could one day help our doctors better understand, track, and ultimately protect the future of our brains.